Okay. Now, in last lecture, we have covered that PLD part, right? So we have studied the PLD. So what do you mean by PLD? PLD is a device which contains n number of gates, n number of flip-flops, right? And what is structure of PLD? It has AND array logic as well as OR array logic. Now, depending upon the which one is programmable, again that PLD you can categorize into 5 types, right? If both are fixed, AND array is also fixed, OR array is also fixed, then it is a ROM, read only memory. If both are programmable, that means if AND array is also programmable, OR array is also programmable, then what you can say, it is a PLA, programmable logic array. And if AND array is programmable and OR array is fixed, then it is PROM, right? Programmable read only memory. And if and array logic is fixed one and OR array logic is programmable one, then it is a PAL, programmable array logic. Okay, so you have to remember this thing. So that part we have covered. Then we have discussed about the ASIC, application specific integrated circuit, right? So we have discussed about ASIC also, application specific integrated circuit. Then we have compared about the ASIC and our normal PLDs. So that comparison also we have studied. Now in today's lecture, what we have to study? We have to study different architecture of FPGA and CPLD that are available in the market. So already we have even discussed about the category of integrated circuit, right? Full custom, semi-custom, and then programmable logic. And in that again you have CPLD and FPGA. So these two categories are comes under the PLDs, programmable logic devices. Okay, so this is about the classification. Now we have to go for the different CPLD and PLD architecture of some commercial devices that are being used in the industry and to develop different applications. So Altera and Xilinx, these are the two leading companies. They are manufacturing different CPLD as well as FPGAs, right? So Altera Flex structure, it is a FPGA, particularly Altera is a company. Flex is the name given to that product. So Altera Flex is a FPGA category. So you have Flex 8K, Flex 10K series available in the market. Then Altera Max. So Altera is again company. Max is that product name. So Altera Max is a CPLD. So you have Max 500, you have Max 700, you have Max 9000 series, 5000, 7000 series. So these are the CPLDs manufactured by the Altera company with different specifications and advancement, right? Again, next leading company Xilinx. So Xilinx also manufactured some CPLDs, right? Xilinx XC7000 is a famous CPLD that is used. Then Xilinx XC9500 family is there. It is also one of the famous CPLD manufactured by Xilinx. Then again, you have XC2000, XC3000 series, XC4000, XC5000 series. So these are the Xilinx FPGA series. Xilinx also manufactured both CPLD as well as FPGA. So these are the FPGA that are manufactured by the Xilinx, right? XC2000, XC3000, all that. So for your syllabus, Max 700, Altera CPLD Max 700 is there. Then Altera Flex 10K FPGA series is there for your syllabus, and Xilinx CPLD XC9500. So these are the what we can say, different CPLD and PLAs are there in your syllabus. So we will discuss that only. So as you know, the CPLDs are just an extension of PAL, right? CPLD is just an extension of PLDs. So it is a more complex, right? It is a more complex than the PLD, and it is a just extension of PAL concept, programmable array logic concept. So more complex PAL, so you can consider that PAL as a CPLD device, complex programmable logic device. Again, you know, PAL is again one subtype of PLD only. PAL काय आहे, एक PLD चाच प्रकार आहे, बरोबर आहे. So CPLD you can know, you can call it as a more complex PAL, that is a CPLD. Okay, so you have to remember this terminology. Then this is the typical CPLD architecture. Okay, now what is what you can see in this architecture? So you have IO blocks, then you have PAL like blocks, right? So 4 PAL blocks you can able to see. Then you have different interconnection wires. So these are the major components and architecture of any CPLD. So it is a general architecture, you can see, right? It has a IO blocks, it has a PAL blocks, and it has a interconnection wires, right? So this total constitutes the any general CPLD architecture. Now we will discuss first that MAX 7000 Altera CPLD, right? So what is speciality of that MAX 7000 Altera CPLD? So this MAX 7000 family, it is actually high density, high performance CMOS CPLD, and that is based on the Altera's second generation MAX architecture, right? So what is speciality of this MAX 7000? It is a high density, high performance CMOS based CPLD, and it is a next version of that MAX architecture. So the basic version is MAX 5000. So MAX 7000 is again advanced version of that, and again MAX 9000 is again much advanced than the MAX 7000, right? So this MAX 7000 devices that are available both in EEPROM as well as EEPROM technology. Both are available in EEPROM as well as EEPROM technology. So these are the some specific point and specification of this MAX 7000 Altera CPLD. Okay, now we will discuss about its architecture. Okay, so what how this MAX 7000 architecture look like? So this is the architecture of this MAX 7000 Altera CPLD. So you can say it has macro cells, right? So it has 4 lab, right? LAB, lab A, lab B, lab C, lab D. What do you mean by lab? That we will discuss later. Okay, then it has IO control blocks, 4 IO control blocks, and it has PIA. It has PIA, that is programmable interconnection of architecture. That means whatever the architecture or that lab are present there, inter IO control blocks present there. So this PI is nothing but, you can say, it is a simply bus. It is a bus that will interconnect each and every block with each other. That will interconnect each and every block with each other. So, and also it has some input global clock, input global reset, then input OE1, input OE2. So these are the some control pins also provided with this architecture. Okay, now what do you mean by this PIA? What do you mean by this LAB? So that we will discuss now. Okay, so this Altera MAX 7000 series, it comprises of logic array blocks. LAB is nothing but logic array blocks. PI is nothing but programmable interconnect array. PI is nothing but programmable interconnect array, and of course IO control blocks. So you can see here, this lab is nothing but logic array block, this PI is nothing but programmable interconnect array, and of course you can able to see the IO control blocks. Okay, now this PIA is capable of connecting any logic array block input or output to any other logic array block. That means, see, you can able to see here, with the help of this PIA, this every logic array block, we can say it's a simply lab A, lab B, lab C, and lab D. So these 4 labs are interconnected with each other through this programmable interconnect array. Okay, Again, I will repeat, this programmable interconnect array is nothing but a kind of bus that will transfer data from one lab to another lab. Okay, so this is the programmable interconnect array, that is PIA. Then it has logic array block, then input output control block. Okay, now, and what is role of this PIA is to connect every single lab to each other. बरोबर आहे. जेवढे काही लॉजिकल अरे ब्लॉक्स आहेत ते एकमेकांना कनेक्ट करायचं काम कोण करतं? प्रोग्रामेबल इंटरकनेक्ट अरे, राईट. ऑल्सो द इनपुट अँड आउटपुट्स ऑफ द चिप कनेक्ट डायरेक्टली विथ टू PIA अँड टू अ लॅब्स. बरोबर आहे. म्हणजे लॉजिकल अरे ब्लॉक तर ते कनेक्ट करतं. ऑल्सो हे जे इनपुट कंट्रोल ब्लॉक आहेत, राईट, सो दीज आर द इनपुट्स ऍक्च्युअली, इनपुट आउटपुट पिन्स. So that are also directly connected to the PIA. That are also directly connected to the PIA. So in architecture, you can see that. Okay, that are also directly connected to the PIA. And each lab consists of 16 macro cells, or 2 sets of 8. Right? म्हणजे ही प्रत्येक जे लॅब आहे ह्याच्यात इट कन्सिस्ट ऑफ 16 macro cells. बरोबर आहे, 1 to 16. So each lab consists of 16 macro sets, and that is इन 2 सेट्स, राईट. 8-8चे 2 सेट असतात, टोटल 8-2 16. 16 मॅक्रोसेल्स त्याच्यात कनेक्टेड असतात त्या लॅबमध्ये. प्रत्येक लॅबमध्ये टोटल 16 मॅक्रोसेल्स असतात, 8-8चे 2. ओके, नाउ नेक्स्ट पॉइंट इज in case of this max 7000 lab, it has 36 inputs from the chip wide interconnect. Okay, and 16 outputs to PIA, right? So in case of this max 7000 lab architecture, it has total 36 output, 36 inputs. How? You can again go back to a block diagram. So it has 8 to 16 input pins. Again, it has 8 to 16 input pins, right? Again, it has 8 to 16 input pins. So in all, it has 36 input output, and that is connected via this PIA. You can able to see here. It is a 36-bit input port, and that is connected to a this total lab with the help of this PIA. Okay, and from 8 to 16 outputs from each lab can be routed to the input output pins through the input output control block. From 8 to 16 inputs from the input output pins can be routed through a input output control block to a PI. That means each normally this 8 to 16, right? So that may be a 8, that may be a 16. This 8 to 16 input output pins are connected to this input output control block, and that is again connected via this 8 to 16 bus to this LAB, logical array block. So this is about the architecture of this Altera Max series. Okay, now this is the architecture of this internal architecture. Means now we are just what we can say, observe the external block diagram. So it has a input output control block, then it has a lab, then it has a PI. Okay, but now actually what is the inside circuitry present in that input output port, then what is that what we can say, lab, logical array, then programmable interconnect array, PI. So we have to look into this diagram. So this is the internal structure of the Max 7000 Altera CPLD. Okay, now as I told you, it has 4 control pins, right? It has a global clock input, global clear input, then output enable signals. It is to OE1N and OE2N, right, to the output control block. So it has total 4 control pins: global clock input, then global clear input, and 2 output enable signals, OE1 and OE2. So these are the 4 external signals to control the CPLD, right? So this is about the external inputs. Then what is this structure of this typical lab, that is logical array block? So as you know, it has a 16 macros in a group of 8. Okay, so these are the macros, array of macros. You can say it is a 16 in a group of 8 and 8. Okay, it is connected to this PIA, programmable interconnect array. Okay, as well as it is connected to this input output control block. Okay, and it is kind of product term sharing. Sum of product or product of some architecture is there. This is the again connection to the other lab with this PIA, and this is the connection to the other input output pins on from input output pins. You can transfer this data to other lab or other input output pins, or it can receive that data from other input output pins. So this is again a typical structure of this logical array block. Okay, again this is the again broad view of this macro cell. म्हणजे आपण हे जे इथं काय पाहिलं, अरे ऑफ मॅक्रो, मग या बॉक्स मध्ये हे जे तुम्हाला मॅक्रो सेल दिसत आहेत त्यात मग त्याचं आर्किटेक्चर कसं असतं परत, तर ते हे असं असतं. म्हणजे त्या परत एका मॅक्रो सेलचं आर्किटेक्चर कसं असतं, लाईक धिस. सो इट हॅज दॅट PIA, then it has that local lab interconnect, then different gates you are able to find here, then product select matrix is there, product or sum of product, then it is D flip flop is there, then different gates, not gate, then buffers are there. So this is typical architecture inside that macro cell. बरोबर आहे. म्हणजे हे एका मॅक्रो सेलचं आर्किटेक्चर झालं. असे किती असतात एका लॅब मध्ये, 16. असे एका लॅब मध्ये किती असतात, 16, राईट. So this is the 16 macros are there in one logic array block, right? So in all total 16 fours are. That many macros are there in max 7000. Okay. So this is max 7000 Altera CPLD. So each macro cell comprises a set of programmable AND plane that feeds the OR gate and programmable flip flop. Okay. So this is about the architecture. Then the flip flop is configured as a D type, JK type, S or SR type, or can be transparent, right? So flip flop you can configure as a any type, D type, then JK flip flop, SR toggle, or it can be a transparent flip flop. The number of inputs to the OR gate in a macro cell is visible. The OR gate can be fed from any or all the 5 product terms with the macro cell, and in addition can have up to 15 extra product terms from macro cell in the same lab. Okay, because you know, in one lab how many macros are there, 16 macros are there. So you can have what you can say, any 5 product terms, or you can use total 15. That means 15 extra product terms also you can use within a single macro. Okay, in that lab, within that lab in a single macro you can use the 15 extra product terms also. Now the product term flexibility makes the max 7000 series logic array block more efficient in the chip area. That means actually the space required for this max 7000 series lab, it is very less, means the area is reduced, right, with the help of this max 7000 architecture as compared to the max 5000. That is the original version of Altera CPLD. That is the very basic version. And what is advancement they have made in this max 7000? So they have reduced the chip area. So this is the advancement they have made with this max 7000 Altera CPLD. Okay. So next is this is about the Altera 7000 max CPLD. We have studied its architecture, then basic functional blocks, then 4 control pins, general global clock input, then global clock clear, and 2 output enable pins, right? So this is about this Altera max CPLD. So next we have is a Xilinx CPLD, that is XC9500 series. Okay, XC9500. This CPLD is developed by the Xilinx. Okay, and the previous one was developed by the Altera. Okay, so this CPLD we will discuss in next lecture. Today we will stop here. Okay, in day we will discuss only one architecture, so that you can have the better understanding, and also our speed will be also reduced. So this is the Xilinx CPLD XC95 family. This part we will discuss in tomorrow's lecture. Today we will stop here. If you have any query, you can ask me.